Okay. From today we studied propagator. Before we studied propagator, we briefly reviewed the time-dependent perturbation theory. Time-dependent perturbation theory is a theory to consider the interaction between particles that has a short that happen in a short distance and during a short period. So initial state and final states are considered to be free particles, and that they have an interaction for a very short time in the short area, small area. So we expand the whole result in terms of the free particle eigenstates. So we introduced the total Hamiltonian is a sum of free particle Hamiltonian and the interaction potential. And H0 is the free particle Hamiltonian. In the non-relativistic limit is p squared over 2m. And it can be extended to the relativistic case, but let us just consider simple case first. So let us assume phi n is the eigenstate with the energy En, and its normalization is delta mn. And here V is the interaction potential. So we want to find the final state wave function at t goes to infinity when the initial state wave function is prepared to be a monochromatic state with the energy Ei. And phi has the spatial contribution only, so spatial oscillation vector is included in here, and time oscillation is factored out. And Schrödinger equation, full Schrödinger equation is like that. We substitute the initial state and find out the final state expansion. We would like to find the coefficient of AK that is either ith component or not. If it is the ith components, then the interaction does not happen. So the final result is proportional to delta Fi. So the initial state is same as a final state. But if we consider V is a very small quantity that can be expanded in powers of V, and we just make a linear approximation by considering the free linear term only, then this equation can be solved order by order. That is called the time-dependent perturbation theory. In the previous classes, we already have derived the details of the results, and I just copied the final result. That is just without interaction and interaction of order 1. So that is integral from minus infinity to infinity and over the space. I assume this potential is localized in a small area. So I is the initial state that is a well-prepared initial state, and the final state can be arbitrary, and it has the non-zero result once I to F matrix element is non-zero. Okay, so let us consider S matrix that has a whole kinds of these kind of interactions. And if I know the full theory, full matrix, S matrix, then what I need to do is just multiply the initial state wave function to the S matrix, then I can find the final state wave function. And let us just consider the T matrix T. The T matrix is just order V, and just cut off the whole expression in order V only. Psi, right. If I copy this result, then this is T, so I multiply C here and divide it by C. So minus I over H bar C, and the four-dimensional integral of this function. And let me call this one multiplied by I is interaction Lagrangian density function. because it is integrated over the 4-dimensional space. After the integration, we find the potential. So it is good to define it to be the Lagrangian density function. And this interaction must preserve the probability conservation. So initial state wave function, to find we can find the initial number of state and the final number of state, that the whole sum must be conserved. So this constraint will give that S dagger S is identity. If it's not the case, the probability disappears. So if the probability is conserved, then because I have this expansion in order V has vanishing contribution, so T must be anti-Hermitian. If I pull this I out, then if I pull out this I, then I is pulled out in here, so Lagrangian interaction Lagrangian must be Hermitian. Suppose if we consider as a simple case, the potential is independent of time and is depending only on the spatial component, and then the integral becomes simple. First we define the spatial integral after factoring this time oscillating vector out to be VFI. Then T matrix element from initial to final state is expressed like that. It is just copied from here. And because we have defined this is VFI and potential is independent of time, then I can pull these whole factor out in here, and remaining integral is the time integral over this. And this is, if the time is sufficiently long enough, then it becomes a delta function. So this is 2 pi delta EFO minus EI divided by H bar, right? And if I pull this over factor out, then I can multiply H bar here, so the H bar cancel. And this is the final result. And what we can think about one more step, the potential V can be interpreted to be in terms of momentum space potential. This just a Fourier transformation to the momentum space. The reason why we introduced momentum space potential is that everything in here, the initial state and final state, are momentum space wave function, right? They are well defined in momentum space, but in position space it is very complicated. So it's better to replace this, even though the potential is expressed in configuration space, it is good to replace with the momentum space expression. Suppose initial state wave function is just a free particle wave function. We know that answer, this is overall factor normalization that can be determined later. This guy. And final state is this complex conjugate with the final state normalization and exponential I pf dot x. So let us substitute these factors into the matrix definition of VFI. Then I find the overall factor product Ni NF, and I have momentum space integral and momentum space potential and oscillating vector in the spatial part, and they are all they are depending on x. So I factor this x out, and then what's happening is that where is it? Where is it? Where is it? I have integral over this space is missing in here. If I put this d cube x, then this guy is what? Three-dimensional delta function 2 pi q delta pf. This is three-dimensional delta function pf, p, and pi divided by h bar, and I have cube, h bar cube out, that cancel this 2 pi h bar cube exactly. And final result is a product of the normalization of the wave function and momentum space potential. And this one shows that potential carries some momentum. In case the initial state momentum is the same as the final state, if they are exactly the same, like delta Fi case, this one does not carry any momentum. But even though the momentum in previous case, the second term, if I consider the second term, energy must be conserved. So our constraint is that this guy P F absolute value is equal to Pi absolute value, right? Even though these two momentum has the same magnitude, their direction can be different. So initial is like that, and final is like that. If I subtract final, this is P of the potential. So the momentum conservation is still valid because potential may carry the three-dimensional momentum. So the whole expression preserves energy and momentum simultaneously. That's it.